Hello everyone, I'm Norman Welberger. We're looking at the sociology of pure mathematics, investigating just how the social aspects of the subject direct its movement. Today we're going to continue with our discussion of the 19th century and introduce a very important figure, Bernard Riemann, who proposed an ambitious new theory of metrical structure in higher dimensions. It became very important for Albert Einstein's general theory of relativity in the early 20th century. And it also introduced all kinds of new ideas about the nature of space, and as we'll see today, also a little bit about the nature of arithmetic, which ends up getting involved. So he's famous for introducing things called Riemann surfaces, which are two-dimensional surfaces, which arise in his work in complex analysis. That is, function theory in the complex plane. And we're going to be talking a little bit about that and give you a very important example, the Riemann sphere, which is really interesting. So he introduced this more abstract idea of the Riemann tensor or metric, and ultimately that led, after many decades, to people slowly coalescing towards the modern notion of manifold, which is these days sort of the preferred way of thinking about the possibilities for the shape of higher dimensional geometry. In my view, the theory of manifold really needs to be looked at very carefully. To me, it's a suspect notion, although most of my fellow pure mathematicians will not agree. So ultimately, we want to address this. So Riemann is a very important figure in this discussion. Underlying this development is a deep philosophical question as to what is the real nature of the space in which we live in. This is a knotty problem to get one's hands around because, what is space? How do we even start to study that? Typically, physicists are looking at the physical space, but they are motivated by looking at things inside the space, like matter, objects, forces, trajectories, and so on. There's also a corresponding notion of mathematical space, which is built up from these various possible geometries that we've been talking about. So each of these geometries provides us with at least a potential framework for modeling the physical space in which we live in. Now, on the physical side, we have these objects. We have rulers and protractors. We can talk about motion. We can look at a swinging pendulum or the force between two objects, or we can talk about the motion of the planet around the sun. So these are all aspects of space because space is the environment in which all these things are happening. But if we strip space from the particles and the possibilities for measurements, then it's much more amorphous as to what actually we're talking about. And in the 20th century, of course, with modern physics, this becomes a crucial, really knotty question as people start to realize that the essential sort of small-scale nature of space is really complicated and probably has some kind of quantum limits that prevent us from drilling down beyond a certain point. And also that on the large scale, things become really strange, and then again there we run up with limits against what we can actually do. But okay, so aside from these things, there's sort of mathematical things or mathematical objects which somehow bridge the gap. They're mathematical things in some sense, but they're occupying physical space, like a platonic solid, like a cube, or a sphere, or maybe a little bit more complicated, an ellipsoid or a hyperboloid, one of these quadrics that we've talked about. There's curves. There's the idea of the plane and a grid, or maybe in some higher dimensional version of that. And then there's other kinds of shapes that one can start studying, and that in the 19th century people became more interested in. For example, this thing here is a donut or a torus. Here is a more sophisticated version of a torus or a donut. It's like a donut with two holes in it. Okay, this is the kind of object that became quite interesting in Riemann's theory of Riemann surfaces. So there's all kinds of possible, approaches to this nature of space. But one of the things that Riemann, I think his work sort of opened up is the idea that there's a kind of a local question. like if we just look at, some small part of our space, what is the nature of that? But there's also a global question, which is quite different from that, which asks about the large-scale structure or geometry of space. Like, is it shaped like this in some sense, perhaps in some higher dimensional fashion? Is it shaped like this? Is it shaped like this, shaped like this? So when we try to get a picture of the entire thing, ideas of Riemann start becoming involved in that they give us a language for talking about the shape of the space in which everything is happening. All right, so I do want to give you a more precise feeling for what's going on here. So I want to introduce this Riemann sphere, but we're going to do it sort of one dimension at a time. And I'll start with the planar version, which is more familiar and it's easier to understand, but already some really interesting arithmetical consequences arise, and the role of infinity becomes very interesting. Okay, so let's look at the unit circle in the xy plane, and we'll think about parametrizing it in a slightly different way from usual. Usually we sort of start at this point here and draw lines through it and parameterize things in terms of a parameter on this vertical axis. Now we're going to look at the North Pole up here as being the point that we're looking at things from. So we're going to draw lines from the North Pole to various points on the horizontal x-axis. Say that one there or that one there. And where these lines then meet the circle is going to be what we consider the transform of the point on the x-axis. Okay? So we're defining a mapping S, standing for stereographic. And S of x, so it takes this point here on the x-axis and sends it to the corresponding point on the circle. And here is the formula for it. The x-coordinate is 2x over 1 plus x squared, and the y-coordinate is minus 1 plus x squared over 1 plus x squared. So for example, here x is just maybe a little bit less than a half, and then if you plug in x equals a half here, then you're going to get a point which is the x-coordinate is positive, the y-coordinate will be negative, and it'll be at that point there. Now, an interesting feature of this transformation is how it relates the image of a point x and the point 1 over x, the reciprocal, okay, which is on the other side of the point 1. So here, if x is a little bit less than a half, then 1 over x will be a bit bigger than 2. And I'm claiming that if you look at the image of x and the image of 1 over x under this transformation, that they end up being aligned. The line joining them is parallel to the y-axis or perpendicular to the x-axis. This is an interesting sort of feature of this stereographic projection. Okay, so what can we do with this? We can use this to rethink some things about the number line. So here's our usual number line, equally spaced points 0, 1, 2, 3, etc., marching up, and negatively minus 1, minus 2, etc., going in that direction. So now what we can do is we can use this S mapping, okay, this mapping S that we're just talking about here. We're thinking of the number line as being just a copy of this thing here. And this S mapping is allowing us to map the points on this number line to points on the circle. Okay, with the point 0 getting mapped down here, the point 1 getting mapped to where it is, the point a half getting mapped somewhere over there, point minus 1 being mapped over here, the point 8 over there, for example, will be some point up here, that may be there, point minus 11 way over here will be some point over there. Okay, so this is in mathematical terms, this is sometimes called compactification. We're compactifying the number line by sort of wrapping it around in a highly nonlinear fashion, but that gives us room to remarkably add one more point, infinity. That's really a special feature here, right? We're getting this new point on our extended number line, or number circle, we could say. So this is a pretty interesting because, of course, traditionally we think of infinity is playing sort of a strange kind of role. Does infinity really exist? But anyway, here we're seeing it in this compactified number circle. So this is the basic two-dimensional version, of which the Riemann sphere story is then the three-dimensional version of that. Now, I can't help but share with you an interesting aside, some more information about this planar stereographic projection, which connects it with the inversive geometry that we've already talked about, okay, where you're inverting in a circle. So this planar stereographic projection, the mapping I called S, can actually be thought of as inversion in a suitable circle. So here's that unit circle that we've just been talking about. Here's the x-axis, and here again is the same picture that I've shown you already. There's a point on the x-axis, there is S of x, there's the image of it on the circle. Here's another point, here's the image of it on the circle. What I'm claiming now is that this mapping, okay, from points on the horizontal axis to points on the circle, actually can be thought of in terms of inversion in this green circle, whose center is the point here, the North Pole, and which passes through this point here and this point here, the points 1 and -1 on the x-axis. So that's saying, for example, that if you look at the image of this point here, do you remember how inversion works, right? So the inversion of this point in this circle. One way of thinking about that is you create tangents to the circle through that point, and then you join up those tangent points, and then where that meets the line from the center of the circle to the given point, that is then the inverse of that point there. So that's pretty interesting, and in fact, so then it turns out that the property that I told you that you could investigate, that the relationship between the images of this point and this point, if they're reciprocals, ends up being reflection in here, is then a special case of a much more general property that inversions have, which is that they respect themselves inversion in circles. Okay, so anyway, that's a little bit of an aside for those of you with a little bit more experience, showing again that mathematics is a really all-embracing subject. All aspects of it sometimes sort of interact in surprising ways. It's not just that they're sort of these separate disciplines, but they actually do interact, and it's actually a very rich story. So this view of the number line as a number circle with an additional point at infinity is quite disconcerting, perhaps, because it does suggest that there might be a valid arithmetic that does actually include a new number called infinity. And so a natural question is, to what extent can this be done? To what extent is there really a consistent arithmetic that does involve a new point called infinity? And does one have to, go against the laws of logic in order to do this? So many of you will know that I'm sort of an opponent of a lot of sort of infinite thinking in mathematics. But some people sometimes call me a finitist, which is not really the case, I think. I'm quite happy to entertain notions about infinity as long as we can be completely precise about what we're talking about. I don't object to using infinity in some context. For example, here, this is quite a reasonable context. There's nothing magical about infinity because we're able to pin it down very precisely in terms of the geometry of this circle. What I do object to is the claim, the specious claim, that we are able to do an infinite number of things, okay, and get outputs which we can then use for other calculations. That is a different use of sort of infinite things, and that is, I think, hugely problematic logically. So what about this question, is there actually a consistent arithmetic which includes infinity and sort of extends the usual arithmetic with ordinary numbers? And the answer to that is partly. And so there are a couple of operations that we can introduce in a consistent way, but there's others which we can't. And a way of thinking about this in order to try to make sense of some equation like 2 plus infinity equals infinity. What does that mean? So one way of thinking about that, and to try to convince yourself that this is sort of consistent with the usual arithmetic, is to think about maybe not infinity immediately, but rather some point on the number line which is pretty close to infinity. So a big number like 8, but much bigger, which is big positive, or a big negative number. And ask yourself, okay, if we're moving towards this point infinity on this number circle, does this law still work? In other words, suppose you took 2, the number 2, and you added some really big number, like a million. A million is really close to infinity up there somewhere. The result of that is 2 plus a million, or a million and 2. Where is that going to be on the picture? Well, that's also going to be close to infinity. Okay? And so the closer you are to infinity, in fact, it doesn't matter which side you are, if you add 2, you're also going to be close to infinity. And that is then the starting point for thinking that you can probably make this a valid kind of arithmetic. Similarly, it's not too hard to show that 3 minus infinity equals infinity. That's a reasonable kind of thing. 5 times infinity is infinity. If you take some big number, like big meaning close to infinity, so either a big positive number or a big negative number, and you multiply it by 5, well, you're going to get another big positive or negative number. If you take the product of 2 such big numbers, you're going to get another big number. And here's a really interesting one. Okay? You've all been taught since early days that it's completely forbidden to divide by 0. It doesn't make any sense. So, but I'm claiming that, in fact, this does have a consistent meaning in this larger arithmetic where you're willing to include this infinity. And what's the meaning? The meaning is that if you take 1 divided by some number which is close to 0, either close on this side or close on this side, well, then the reciprocal is going to be a big positive number or big negative number. And as you get closer and closer to 0, well, the reciprocal is getting closer and closer to infinity. So it becomes consistent to say that 1 over 0 is infinity, and similarly 1 over infinity is 0. However, this is not a complete consistent arithmetic because infinity times 0 cannot be so easily pegged down. If I take a really big number close to here and a really small number close to here and I take the product, I have no idea with just that information where that product is. That product could be very big, it could be really small, it could be somewhere in between here. Right? So this one here is not a valid rule, in at least in the obvious way, in this geometry. And similarly, infinity plus infinity doesn't work consistently because this possibility has to include not just the sum of 2 big positive numbers, which admittedly is a big positive number, or the sum of 2 big negative numbers, which is, of course, another big negative number, but also the sum of a big positive number with a big negative number. And if you take that combination, like 8 plus minus 10, you're going to get minus 2, which is nowhere necessarily close to infinity, even if the 2 ingredients were close. Okay? And similarly, infinity minus infinity is not defined. But so it's intriguing, and in fact, with Riemann's 3-dimensional version of this sort of partial arithmetic with this concept infinity ends up playing actually a crucial role in the function theory that he is studying. So it becomes not just an interesting kind of academic question, it becomes a central feature of the complex function world. So let me now explain to you Riemann's idea of the Riemann sphere, where he does what I've just showed you, but basically starting with the complex number line to begin with, rather than the usual number line. So here is the usual complex number line, which is to us a plane. It's got an x-axis, a y-axis, and a typical complex number, x plus iy, which we may call z. It's the usual format for it. Z equals x plus iy, has a component in this direction and a component in this direction, and crucially in this direction here, there's an I that magical new number that has the property that I squared is equal to -1. So Riemann is going to do the same thing that we kind of did, but he's going to take this complex line, which is really a one-dimensional line, and make it horizontal, okay? And then he's going to, over the origin 0, he's going to make another axis, okay? Let's call this the w-axis, okay? So there's the w-axis here, and horizontally there's this plane, we'll call that the z-plane. And there's x and y coordinates in this horizontal plane. So this plane is the one that you're seeing here. So there's the point 1, there's the point -1, there's the point I, there's the point -I, okay? So this circle here that you're seeing here is the usual unit circle in the complex plane. And now Riemann says, okay, now let's take this sphere, okay? The sphere, which is centered at the origin here, okay? And which has an equator which is created from this complex plane. And here's the north pole of that sphere. And now we're going to do the same kind of thing that we did. Now this is like the stereographic projection of the sphere. But that then allows us to basically coordinatize the points on the sphere by complex numbers. Because the numbers in this horizontal plane, they are basically complex numbers. Okay, so we start with some complex number, let's say let's say this point here. Okay, so it's a little bit hard to see. So this point here, we'll suppose that this is a point on the horizontal plane. Okay, maybe we could think about it as being out here. Okay. Or actually, in this diagram, it would be slightly inside, and then you connect that with the north pole. Okay, you get a line, and where it meets the sphere, it comes out the sphere, that's S of the point Z that you're starting with. Okay, so what that ends up doing is allows us to map the sphere via the plane with the addition of this additional point at infinity. So we're moving from the complex number line to the complex sphere, or it's called the Riemann sphere, which is now a sphere whose points are indexed by complex numbers. So for example here, that might be the point 1, that'd be the point -1. Okay, along this circle here, there would be I on this side and -I on this side. Okay, and you know, points over here might be like 3 plus 4I, or 18 plus 27I, that kind of thing. Okay, and in addition to the regular complex points, there's the single north pole up here, this new point, which has now the name infinity. So this is really interesting because Riemann is interested in the idea of functions on the complex plane, and this gives him a way of not just visualizing, but also sort of connecting these functions with geometrical objects. So let's have a little discussion about functions. The notion of a function is a hugely subtle one and is full of pitfalls and logical difficulties, having to do with what the actual explicit concrete definition of a function is. But loosely we can think of a function in the usual way. It's something that takes some input of a certain kind and outputs something else, possibly a different kind, or maybe possibly the same kind. Now, in high school, you're used to thinking about arithmetical functions given, say, by polynomial equations, like y equals x squared. Okay? So let's just remind ourselves about the different ways that we think about such a simple function back in high school. Perhaps the simplest way is to think about creating a table of values where we record different x's and different values of the function applied to those x's, in this case x squared. So 0 squared is 0, 1 squared is 1, minus 1 squared is 1, 2 squared is 4, minus 2 squared is also 4, 3 squared is 9, etc. So we could create some points like that. And then we could take a table like that and try to create a more visual representation of the function by essentially plotting those points in a two-dimensional plot. So the point 0, 0 is right there. 0.11 is right there. So what we're doing is we're replacing the x squared with y. So, or interpreting the x squared with y. So the y component here is the x squared value, while the x component is just the original value. So minus 1, 1, that's that point there. 2, 4 is that point there. Minus 2, 4 is that point there. 3.9 is up there somewhere. There is, however, another way, a third way of visualizing what a function is, which is to think of it as a mapping or a transformation of the underlying space. So here's our number line, and we can think about this function y equals x squared as taking a point on the number line and moving it physically to another point. So for example, 2 gets sent to 4, 3 gets sent to 9, minus 2 gets sent to 4, minus 3 gets sent to 9, while 0 and 1 are sent to themselves. So visually, you could kind of think of taking this number line and sort of folding it over like this. This negative part gets folded over onto the right side, and then there's also a corresponding stretching going on. All right, so these are three different views of the usual function y equals f of x, which is x squared. So now let's look at that same function, but now thinking of it as a complex valued function. So something that takes complex numbers and sends them to complex numbers. So we might write w equals f of z, where f of z is z squared. Now we're thinking about z as a complex number and w as a complex number. So we can visualize that, at least partially, by creating a table like we did last time, but now with values of z and w ranging not just over rational values, but also complex values. So we can include something like I squared is minus 1, or 1 plus I, which is 2I. Or if we square 3 plus I, what is that? Well, the square of 3 is 9, the square of I is minus 1, so that's a total of 8, and twice the product is 6I. So this is another way of trying to get some sense of what this function now looks like. How about if we want to graph it like we did for y equals x squared? Well, that's a bit more problematic because we now need a z plane, which is like the horizontal axis, and we need a w plane, which is now the vertical axis. But each of those are two-dimensional from our point of view. So they don't fit so easily onto a representation like this. But nevertheless, we can sort of still think that, say, a point like 3 plus I, 8 plus 6I is represented by a pair of complex numbers. So that point there, which is this point here, has a z coordinate, which is 3 plus I, and a w component, which is 8 plus 6I. And then when we think about creating a lot of such positions and then sort of joining them up, joining the dots, we end up getting what's to us a surface. It's no longer a curve like it was in the rational case. We get a surface, okay, which roughly we can visualize something like this. And this is the origin of this geometrical, almost topological aspect of function theory that Riemann realized was going on in the complex world. Now, if we go back to the third form of thinking about a function as a transformation or mapping, that becomes actually more useful now because, first of all, we can visualize the complex plane as our Riemann sphere. So there's that Riemann sphere again. And now this function, z goes to z squared, can be thought of as something that moves points from the sphere to the sphere. And what's that going to look like? Well, a good starting point is what happens on the equator, which is just the unit circle. If you take a complex number on the unit circle, say that one's z, okay, then its square will also be on the unit circle and will be a copy of that sector. So you basically double that sector. So as you go around the circle, z squared goes around twice. Okay? So if there's 1, then there's a kind of a wrapping that goes around. The function sort of wraps the circle around itself twice. And correspondingly, what happens to the entire sphere? Well, the northern hemisphere also gets rotated around, but also what happens is that the points on here also start moving up to the North Pole. So if we square something like that, well, it'll move around here, but it'll also get closer to the North Pole. While points in the southern hemisphere, if you square them, they also rotate around, but they get closer to the South Pole. So this is an interesting thing because now we can also augment our understanding by asking, well, what happens to the infinity point? So we can augment our understanding by adding basically the point infinity, and the square of infinity will be infinity in this case. This is one of these situations where this arithmetic actually is defined. This z squared function actually is well defined on the Riemann sphere at infinity. So that's really attractive because now the entire sphere is being transformed. And Riemann realized this was especially useful for more complicated functions like the function 1 over z. Usually in high school, you have a problem with 1 over z. At 0, it's not defined, so you have this sort of gap in the graph. But when you move to the Riemann sphere like this, something like 1 over z, which can also be represented as a transformation, and it has a continuous aspect because the reciprocal of 0 is infinity, and the reciprocal of infinity is 0. So it becomes actually a nice transformation, actually essentially a Mobius transformation, actually, of the sphere. So this is a very attractive kind of thing because it's giving us a larger view of geometry, but also the arithmetic is intimately connected with it. I'm Norman Wildberger. Thanks for listening.